Wait, so this is 13.1 and 2. So are we going to go over 15.1?
An officer went out of the one stall, and just walked right out. And then I went into my work. And then the same officer came in the front and like shaking people's hands. And I was like, I'm not shaking his hand. Just like, don't do it.
All right, let me get started. So let's talk about hyperbolus. So I talked a little bit about the fact that hyperbolic shape describes like certain comets. You can even get into certain particles, how they approach something and then leave because they're being repulsed. They have different magnetism, right? So different magnetic fields. So that's some of the uses of these. The main difference, so here's a hyperbola. And you can see the main difference here, right? Between this and an ellipse. Subtraction. So the reason, and a hyperbola will, and this one specifically would end up looking something like this. And these just go forever. So whereas I would call a hyperbola contained, this is obviously not contained, right? So this is not part of this. I should make that dotted. You'll see in a minute. We can always talk about the associated ellipse. So remember how I talked about ellipses. If I said at two positive numbers that had to be 9, you can't go beyond 9. So it's contained. Here, if I said, give me two numbers that when you subtract them, you get 9. Two positive numbers. When you subtract them, you get 9. 18 and 9. 9 and 0, right? Could I go up to 900 here?
Yeah.
Of course, as long as this is what? 891. So, could I go as high as I wanted to?
Yeah.
Yes, and that's related to why this is allowed to get larger and larger and larger x and y values, is because when I take a difference, they just have to be the same distance apart. I don't care how large. A billion, as long as this is a billion minus 9, they'll be 9 apart. All right, how are we doing so far? So I really want to understood why the graphs kind of look the way they do. Contained versus not contained. Is as simple as just, do you understand how to do numbers? Yes, we do. So that's why it makes sense. All right, so now let's drill down to the nitty-gritty of how to create this picture. More specifically than just that. And real quick, do you guys see? Now watch. If I ask you, what axis are those sitting on? Does that make sense? What axis are those sitting on? The x-axis. Does that make intuitive sense? Mm-hmm. What part of this do you think told me that it would be sitting on the x-axis? Which part is negative? The y. I like it. So, what is this missing? What kind of intercepts is this missing? It has no y-intercepts. And how do you find the y-intercept? You let x equals 0. If I let x equals 0 here, could that ever be true? Do you guys see what this says? The opposite of a positive number, could that ever be equal to positive 1? What's true about that? That's always positive, isn't it?
Yeah.
So could negative that ever equal positive 1? No. I really want, again, there's a lot of different ways you can figure out why it makes sense that things look the way they do. This has no y-intercepts because I can't let x be 0. If x were 0, the only way to make that true is to have complex numbers. And I don't want to graph complex numbers, so we don't let that happen. All right, maybe. So what would it look like if it was this? What do you think it would look like? It would be like that, you just look at it like that. All right, so it's going to be sitting on the y-axis instead. Maybe. Where do you think the foci would be? What intuitively tells you where? So the focus, when it gets closer to something, it makes it more curvy. So what's inside the hyperbola? It's a little weird. Inside the hyperbola would be there and there, for example, or here and here. So Halley's Comet, it's not hyperbolic, it's back, because it comes back, right? But the focus is always going to be inside the curve. So that the foci there are inside the curve. For an ellipse, it's inside the curve. Okay, I like it. Maybe. Maybe. Okay, so that's generalizations about what hyperbolas kind of look like. Now let's get into the real nitty-gritty. What do you think was going to tell me how far to go left and right? What part of this do you think is going to tell me that? Very specifically, in this case. The A value, specifically. I like it. I know somebody said that, and it's just hanging. And then here, same thing, right?
Yeah.
I can't remember, the book, I think, switches the A and the B and crap. Stupid. What do you think, I know I keep saying I'm going to do nitty-gritty, I'm not going to do it yet. What do you think the focus equation is? Ellipses have a plus or a minus sign in it, and they have a, for the equation of ellipse, it's x squared, a squared, plus y squared over b squared, for an ellipse, right? And its focus equation has a minus. This has a minus in this equation, so the focus is probably going to be plus. And that, of course, I know looks like the Pythagorean theorem. It's sort of related to it. It actually is related to it, but okay, maybe. And think about it. If the focus, if this distance, can somebody tell me how big that distance is? You can do it. You can do it. No. This is the equation here, right? It's A. I like it. And if the focus has to be a little further away, doesn't it make sense that I want to add on top of that so it's further away? That's why the equation has to be a plus sign for the hyperbola. So that's the way I remember for the hyperbola. For both ellipses and hyperbolas, these signs are different. Okay, maybe. So let's do a specific example, and then I'll let you guys attack number 2 on that handout. So let's do this. Let's see. So I just got to pick nice numbers here. Let's make this. Let's just make this x squared. I like it. Yeah. Gross. So there's a really nice way. I'm going to show you the process. So hyperbolas are definitely a little more work than ellipses or parabola or circles, because they're contained. So the curvature of it it just naturally happens when I connect all of the dots that I've made. Here I don't have that. The curvature is kind of important. What's the curvature? I'm going to show you a way to make sure that you get the right curvature. So help me out. What's in the x direction? What am I going to do? How far am I going to go? 1. All right. 1 up and down, left and right. You can do it, Jeff. What about in the y direction? And I'm going to go 7 up and down. Now, a really good question would be, all right, I know this is going to look like this because it's positive x squared. That's how I can figure out where it's going to sit. So this is related to the 1. This seems to have nothing to do. Do you guys see that? It's like 7 doesn't tell me shit, but actually it does. You'll see here in a minute. All right. What else can we do? Let's just go ahead and figure out the focus since we have everything we need here. So the focus for this one's really nice. It doesn't matter who you put first, you're freaking adding. So c squared equals 1 plus 49. Right? A squared plus b squared. So c squared equals 50. So c equals square root of 50.
45.
Yeah, good. Which is 5 rad 2. I like it. Cool. All right, so we figured that out just because we could. So here's the nitty-gritty detail. Let's see. So I want to go 1 left and right. I did. Yay. So I put actual dots there because that's really where the graph is. So when I go 7 up and down, I'm going to put dots there. No, I'm just going to put like a little X, or whatever you want to put there. Little open circles. Yeah, I normally put little open circles. I use X's for my foci. Now here's what's cool. If this was a plus sign, do you see how I would just go, whee, and I'd be done? So every hyperbola has sort of an associated ellipse in the middle of it. Right? So if this would have been turned around, I would be making a picture like that. But I'm doing this because that's the positive part. Okay, cool. There's a lot of little things here. Okay, so here's what's really nice to help me figure out, does it look like this? Is that really skinny or is it really fat? What you can do, this is kind of freaky. Does everybody see how I'm making this little box? All I did was, that tells me how far it is that way, that tells me how far it is that way. I make this little box. Go with me. And what happens with hyperbolas, what tells them how they move, there's these little asymptotes that they have to get close to. That's what tells them how to move. And we're going to make the asymptotes, we go through the corners of the box. This is how it always is done. If you go through the corners of the box. So from the center, and why is the center here?
Because there's no coefficient.
No shift, I like it. There was no shift inside, right? No x minus 1 or y plus 3. So I just draw this little, right through the corner, right through the corner, right through the corner, right through the corner. Cool. So this is going to be really fat, because what I want to do now is I want to start here, and I got to approach that asymptote, got to approach that asymptote. I've got to approach from here. I want to approach that asymptote and approach that asymptote. It's really fat. So if it would have been, if these would have been turned around, it would have been a lot skinnier. It would have been here and there. So when I draw that box, draw the asymptotes through the corners, this is what guides me. This is the guide for how fat or skinny it is. That's all that is. It's just a way to see how fat or skinny it is. In astronomy, it normally has to deal with how strong the gravitational forces are that's involved that determines how curved the flight path is going to be. Right? So where is the focus? What is 5 rad 2? It's roughly 7. Try it out. Tell me if I'm right.
7.07.
Yeah, I like it. Cool. And where do you think the foci are going to be? Everything about this problem is on the x-axis. So this gets a little bit freaky. And remember what I said. The closer the focus is, the narrower it should be. So why does it make sense it's really fat? Because where's the focus? Way out there at 7. So that's why it's really fat. If I push that in, it's like that. You ever seen that video of the guy that gets a cannonball into his belly just to show off? Do it. Boom. He's like, boom. So if I push it in, it's like, oh, oh, ah. I can't do anything about dirty minds out there. All right. Cool. Freaky. What the hell? Shit. A little more involved than ellipses, but you can see where the ellipse would sit. But I got to do a little more work to get this bad boy to show up, and this is nice. This is a guide for how what the curvature would be. That's what that really does. So if it would have been turned around, this would have been there, this would have been there, this would have been the answer. It would be a lot more. Can I put this on here without you guys freaking out? If this was turned around, it would look like this. Isn't that a lot skinnier than this? Because the focus here, isn't that 7 already? And what was it, 7 point something? So the focus would have been right there, pushed in. Whereas over here, the focus is way out at 7. It's like, okay, all right. That would be this. No? Yes?
All right. Down, can you do that?
Say again?
But I'm getting weird down every time you do that on here.
Oh. All right. Sorry. I should do sounds only for you. Sorry. All right.
I can't wait.
Do you like the? All right. Sorry. All right. So, moving on from there. If you haven't already tried number 2, try number 2. Just make sure everybody's going to start that off on the right foot. Is it going to be sitting on the x-axis or the y-axis? The y-axis, because that's the one that's positive. Sweet. Go for it. Everybody see this note up here, by the way?
Yeah.
13.3 homework. Yeah, extra credit. Oh, damn, power going out really screwed us over.
What kind of helped us? Because we didn't.
You're on, I know, from your perspective, you're like, less shit to do. You know? You're less prepared for your next class. That's what.
Are the vertices what we count for the x direction and y direction?
For hyperbola, it's only got, there's only one set of vertices because that's the only ones that are on the graph. These are just only exist purely to make this box so I can get the how fat the thing is or skinny. To show you. Oh, cool. Yeah. Oh, good. Okay, good. I like that.